Hello again, this is Dr. Kate, and this is my video on how to do a theoretical titration curve. Now, in the lab for Analytical 1, you need to do a theoretical titration curve for titration of carbonate with hydrochloric acid. I am not going to show you that one specifically. I will show you generally how you do theoretical titration curves, but you're going to have to look up the formulas for your particular titration yourself from the textbook. So we're going to start with the table from the textbook, and this will be a different chapter depending on which edition of the textbook you have, but it will always be towards the end of the chapter on acid-base titration, so it should be fairly easy to find. And what you're looking for is the titration equations for Spreadsheet's table. So this table is full of equations, phi equations they're called, and phi being the Greek symbol here, and phi is indicative of the fraction of the titration that is completed. So phi is equal to 1 when you're at the first equivalence point. If there are multiple equivalence points at the second equivalence point, phi is 2. The third equivalence point, phi is 3, etc. And these equations allow you to calculate the extent of the titration using only the pH of the solution, and then from the phi equation you can calculate the volume of the titrant. So this is a little backwards from the way we do experimental titration curves, where we would typically figure out or measure the pH at a particular volume of titrant added. In this case, we already have the pH and we're calculating the volume of titrant that would have been added to, at that pH. So I'm going to do titration of a diprotic weak acid with strong base, so that's how I've labeled my spreadsheet over here. And when I go to this table, I'm looking for that particular phi equation, and it's right here, titrating H2A with strong base. So this is the phi equation I'm going to need. And in the phi equation, there are two alpha equations, plus we need hydronium, hydroxide, and we need the concentration of the acid, concentration of the base. So the alpha equations, alpha HA and alpha A2 minus, those equations are fractional composition equations, and they're at the bottom of the table. So I'll just scroll down a little bit here. So at the bottom of the table, we have all of our alpha equations. We have it for a monoprotic system, for a diprotic system, and for a triprotic system. Here we're working with diprotic, and notice that all of these formulas use H plus in the calculation. So if you're using H plus in the calculation, then that means that all of those equilibrium constants are Kas. They are not Kbs, even if you are titrating a base. So that's what it says right here. Symbols K1 and K2 for the acid, or K1 and K2 for the base, are acid dissociation constants in both instances. So over in my spreadsheet here, I've got a concentration for my acid. I have the volume of the acid, so this would be my weak acid, what I started with, 25 milliliters of 0.01 molar. A concentration of my base was 0.01 molar, and then I've got 2 Ka. So these you would have to look up for the particular titration you are doing. You should know the concentration of your titrant and the volume of your analyte that you started with, and using your experimental titration curve, you can calculate the concentration of the analyte that you started with. And I also have Kw on here because I will need that for calculating hydroxide. So the first thing I'm going to do is set up a range of pHs. So I'm going to start at a fairly low pH. I'm going to start at pH of 1. I can always change that later. And I'm not going to type in 1, 1.1, 1.2, 1.3 because that takes far too much time and it's silly because this is a giant calculator. It can do that for me. So now I'm going to do a formula. I'm going to say equals because all formulas start with an equal sign. And then I'm going to click on the cell above. And I'm going to say add 0.1. Oh, that's easy. And then I can just copy that down. And I want to get up to a pH of probably close to 13. So I'll just keep going until I get up to 13. You could make the gradation smaller. You could do 0.01, but you're going to have a lot more points if you do that. You're going to have to do a lot more scrolling. So I'm almost at 13. There we go. So we're almost at 14, actually. So that's fine. All right, so H plus, that's pretty simple. That would be, again, a formula. So equals, and it's 10. And then the caret sign for the power, and then negative. And then I'm going to click on pH. Done. And I'm going to copy that all the way down. So to copy all the way down, click on your cell, go to the bottom right corner till you get that plus sign, and then double click it. Okay, next cell over is hydroxide. So the hydroxide is equal to Kw divided by H plus. Done. Okay, copy that all the way down. Hold on a second, what's going on? I've got 0, then I've got an error message, and then they all seem to be the same from there on. So that can't be correct. So if I go back to my original equation, I can click on it. I can see where the cells are, and it says take H plus and divide by KW, or take KW and divide by H plus. Sorry, got that backwards. Okay, but if I go to this one, now this blue cell has moved down. I don't want it to move down. I want it to stay there. All right, I need to use dollar signs. I need to make sure that that blue cell, the KW, does not change. So that's the B8 cell. So I've just put my cursor with the B8 in the formula. And now what I'm going to do is I'm going to press F4. I am working on a PC, not on a Mac. This does not work on a Mac. So if that's your problem, you can either type in the dollar signs or, work on a real computer. So I hit F4, and then it's very easy to remember F4 because 4 is where the dollar sign is on the keyboard. So F4 puts a dollar sign in on both the letter and the number. The dollar signs prevent them from changing when you copy the formula. If I hit F4 again, it's just on the number. If I hit it again, it's just on the letter. If I hit it again, it's on neither. So it cycles through all the possibilities for dollar signs on your cell address. So I want it on both. I hit enter, and then double click this down again. Woohoo, that one worked. All right, so I've got H plus, I've got OH. Now I need the alpha. So alpha for HA minus. HA minus is the amphiprotic species. And so we want to find the alpha equation for a diprotic system for an HA minus. We come over here, it's this middle one, H plus times K1 over H plus squared plus H plus times K1 plus K1, K2. So equals H plus, that's this one, times K1, there's my K1, divided by, now my bottom term, my denominator, has 3 terms in it. So I'm going to open a bracket, and we've got, remove that out of the way so I stop hitting it, H plus squared, so caret 2 plus K1 times, we do have to put the implicit times in, H plus K1 times K2. Close the bracket. We're good. Okay, now, I didn't put any dollar signs in, so the green one and the pink one need dollar signs. So I need a dollar sign there, and I need a dollar sign there, and both of these last two. And copy it down. Second alpha. Well, I'm going to try something here. I'm just going to copy this over, and because the denominator is the same for the alpha for the A2 minus, and then we'll see what happens. So these two have stayed in the right place. This has moved over one, so I'm going to have to, and it's referenced multiple times. So if I move these all over here, now I've got all the right terms, but if I look at the A2 minus equation, it's got K1, K2 on the numerator. The denominator's the same. So here, I've already got K1. Now I just need to put in K2 and a times. And then I'll just go back here and put in the dollar signs. F4. Okay. So that was easy. Copy that down. Okay. Next, the phi equation. So this is diprotic weak acid with strong base. So that is this phi equation here, titrating H2A with strong base. So phi is equal to the alpha HA minus. Oh, and lots of terms in the numerator, so we better open a bracket. So alpha HA minus plus 2 times the other alpha, the alpha A2 minus, minus, open a bracket again, H plus minus OH, close that second bracket, divided by, and now it's divided by CA. So my CA is up here. That number will need dollar sign, so I'm going to hit F4, and that's my entire numerator. So I can close that first bracket. Now divide by my denominator, open another bracket because the denominator has multiple terms, and it's 1 plus, another bracket, H plus minus OH, close bracket, divided by CB, and close the bracket again because that's my entire denominator, and I'm done. Okay. There we go. Oh, hold on. We have some problems here. Did I miss a dollar sign? Let's see. Everything orange should have a dollar sign. I missed that one. And green. So, nope, that's it. Let's see if that worked. There we go. Okay, no error messages. And then finally, VB. So, if we look at titrating H2A with strong base again, we see phi is equal to CBVB over CAVA. I want to calculate the volume of my titrant, which is VB. So VB is phi, so equals phi times CA, which needs dollar signs, times VA, which needs dollar signs, divided by CB, which needs dollar signs. Now I've left the VA, the volume of the acid, so that's what we started with in our titration. I've left it in milliliters, so our VB will be in milliliters. Okay, and I'm going to, I don't want this in scientific notation, I just want it as a number. It is negative, that's fine, we can deal with that later, and I'm going to copy that down. So it does eventually become positive, right? We got some reasonable numbers here. Lots of numbers around 50, so probably our equivalence point is around 50 milliliters. Then it starts to get bigger and bigger, and then we have this number that we can't read, and if we expand that out, it's a huge number, and then it goes back to negative again. Okay, so we're going to clean that up eventually, but for right now, I'm just going to expand this out because we're going to do the graph. So I'll expand that to the full screen, and then we're going to do the graph. So the default in Excel is that your first column is your X, and all of the subsequent columns are your Y's. Unfortunately, in this case, our X is in our last column because our volume is our X. So there's a couple of different ways you can deal with this. You could copy your pH column. So copy this column over to here, and then you would have your X and your Y next to each other. Or you can make a blank graph and then just enter the data yourself. So I'm going to do that. So I'm going to go away from my table because I don't want Excel to automatically make a table or a graph from that. I'm going to insert, I'm going to do a scatter plot, and there's my blank graph, and then I'm going to go to select data. So I'm going to add, and I'm going to put in my X's, which are here. There we go. And then I'll do the Y's. Now to get that whole column highlighted at once, what I did was held down, clicked on the top of the column, and then while holding the shift key, hit end and then down arrow, and that highlighted the entire column. Okay, so I've got all of it now, and there we go. There is our graph. Doesn't it look like a titration curve? But remember, we had that number down here. Remember this huge number down here that didn't make any sense? So that's what's causing this on our graph. And you can see that the scale is silly. So what I'm going to do is the first thing I'm going to do, actually the first thing I'm going to do is get rid of the legend because we don't need it. We only have one set of data. But I'm going to go to format axis. I don't want it to go negative. I want my minimum to be 0. And then a maximum, we said the equivalence point was around 50. I'm going to let it go to 100 milliliters. That should be plenty. And hey, now it actually looks like a titration curve of a weak acid with strong base. It starts low, it goes high. It looks like there's a titration or an equivalence point in there. There's definitely one there. And there's this weird line. What's that? Well, our numbers went positive, 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 hugely positive, and then went negative. So that's it coming back to go negative. So it looks like a titration curve. I'm pretty happy with that. Now I just want to make it a little cleaner. So I'm going to go back to my table here, and if I look at my volumes, it starts out at negative 22, gets smaller and smaller and smaller negative. There's a negative 0.2, and then my first positive number is 0.76. So that happens at a pH of 3.1. Because of the way I set up my pH column, if I go up here and change this to 3.1, now the 0.76 is here, and I have only positive values. That's great. I didn't know what range of pHs I was going to need when I started, so this way I started big and I can narrow it down afterwards. The next thing is if we said we've got this hugely big number down here, which is giving us that weird line in our titration curve. Well, we said it looked like the equivalence volume was around 50 because we had lots of values around 50. So how much further do we need to go? A little bit past 50, so maybe 55, 60, somewhere in that range. So if I come down here, I've got a point at 60.8. That's at a pH 11.1. So I can probably just delete everything from that point on. I'll go back up and look at my graph now. Now it looks pretty good. If I wanted to go back and make it go a little bit farther, I could copy a few more points down and extend this out a little bit more if I wanted to. So we have the right shape of our graph. The next thing that we would do if we were comparing this to an experimental graph is we'd want to check the volume for our equivalence point. So we've got an equivalence point here that's around 50. We have another one here that's around 25. I'd want to go to my experimental curve and see if we had the equivalence points at the same volumes. Then I'm pretty comfortable that I have made a theoretical curve that matches my experimental curve. So this graph still needs to have the axes labeled, so we'll need to put pH here, volume of titrant here. It needs a title, titration, of a diprotic weak acid with strong base. We should include the concentrations if we have them for the acid and the base, and the starting volume for the acid. The concentration of the titrant could appear in the x-axis label and or the title, but it should definitely appear in one place. So that's it. That's how you make a theoretical titration curve. As I said, this is not the theoretical titration curve you need to do in lab. It uses very similar equations, but they are not these ones, so you'll need to look them up in the textbook for the titration that you're doing. Thank you. Bye-bye.